Heyo! Welcome back. In this video, we're going to discuss the properties of kernels. So, how do kernels interact with each other, and how do we create new kernels? You know the routine. Let's derive some properties of the kernel, or the gram matrix K. By calculating the matrix product of the design or basis matrix phi with itself, we immediately see that the kernel matrix is the result of phi transpose phi. Consequently, K is symmetric. The product of the design matrix times any vector B is, by definition, a vector, and thus has a length equal or larger than 0. We can rewrite this using the kernel matrix, and thus it follows that K is positive and semi-definite. So we've seen the properties of the kernel, but does that mean that any function that's symmetric and defines a positive semi-definite gram matrix is a kernel? Well, according to Mercer's theorem, the answer is yes. If any function is symmetric and produces a positive semi-definite kernel matrix or gram matrix in that feature space, then it's a kernel function. That means that there exists a map phi so that the function represents the scalar product in that feature space. We prove this property by explicitly constructing the corresponding feature map. First, we note that because K is symmetric, the eigenvalue decomposition gives us a diagonal matrix lambda with the eigenvalues lambda sub t and an orthogonal eigenvector matrix V. Orthogonal means that the inverse of the eigenvector matrix V is its transpose, V transpose. Thus, we have V transpose at the end instead of V inverse. Furthermore, because K is positive semi-definite, we know from linear algebra that all the eigenvalues are positive or equal to 0. That is, all of the eigenvalues are non-negative. Now, because all the eigenvalues are positive, we can define the feature mapping of the nth training sample as the component-wise product of the square roots of the eigenvalues with the nth row of the eigenvector matrix. Of course, this definition is artificial and probably does not correspond to the original feature space. But if we calculate the scalar product in this strange feature space, we see that we recover the gram matrix, and thus K is indeed the scalar product in this feature space. However, it might be very difficult to prove that a function satisfies the property of positive semi-definiteness. Therefore, one usually does not prove that a function is a kernel directly, but uses rules to build a more complex kernel from functions that are already known to be kernels. Rule 1 and Rule 2 are very easy. Rule 1 is because the sum of two positive numbers is still positive. And Rule 2 is because the product of two positive numbers is also still positive. Rule 3, the product of two kernels, is the toughest one to know intuitively because it involves another definition from linear algebra, namely the Kronecker product. The Kronecker product of two square matrices, x and y, is a block matrix where each entry is the matrix y scaled by an entry from the matrix x. Its use here should make sense if you make sure you understand what this special product is doing. There's lots of resources on the internet that you can Google and find more information about the Kronecker product. Rule 4 is trivial because K sub 3 is already a kernel. Only the inputs are transformed. This changes nothing about the fact that there's a corresponding feature space for the kernel. For Rule 5, we take the square root of matrix B This is possible because it's positive semi-definite and explicitly defined the feature mapping b to the 1/2. By calculating the scalar product in the newly defined feature space, we see that the result is a kernel. Thus, we have shown that all rules produce valid kernels. Okay, that wraps up the properties of kernels. Pretty easy, huh? Up next, we're going to give an example of kernels and summarize the important topics that we've covered so far in this lecture series.